We will see about buck boost converter, which is also called as a inverted output converter. What is a buck boost converter? It can perform both buck and boost operation. That is, it can give you a voltage less than or greater than the input DC voltage. The main application of buck boost converter are solar PV system and battery power system. These two are basically DC sources whose voltage may change. So solar can have a fluctuating DC, and battery voltage, as you know, it changes depending upon the charging level. If you want to maintain a constant voltage across the load, suppose the input voltage is less, you can perform a boost operation and give the required voltage to the load. And if you have a higher voltage, you can do buck operation and give the required voltage to the load. Let us see the operation of a buck boost converter. So you can see here, this converter also consists of switch, inductor and a diode, similar to a buck and boost converters. So the position of these three components will determine the circuit of the buck converter, boost converter and buck boost converter. And we know duty cycle D is equal to T on by T. T is equal to total time period is equal to on time plus off time, and T on is dt and T off is 1 minus d into T. Let us consider the on condition. So in on condition, when the switch is on, the current flows through the inductor, or inductor stores the energy. And if you write the KVL, Vs minus VL equal to 0, so VL equal to Vs, or inductor voltage is equal to the supply voltage. At the same time, I have taken the load current in this direction and capacitor current in this direction. So IC plus I0 is equal to 0, IC is equal to minus I0. So in this period, diode is in turn off condition. Similarly, when you take the off condition, when the switch is open, the stored energy in the inductor will be delivered to the load. So the current flows in this way, where the stored energy in the inductor is delivered to the load. But I have taken the current direction as IC and I0 in this direction, whereas IL is entering this node. Let us take this node equation. So at this node, all the currents are entering the node. So sum of the currents entering the node equal to 0. So from that I can find what is IC. And VL is equal to, this is directly parallel, so VL is equal to V0. Let us write the voltage second balance equation. According to that, in steady state, the average inductor voltage is 0. So take the on condition, off condition equation, equate it to 0. We will get V0 equal to minus Vs into D divided by 1 minus T. So this minus sign indicates that the output voltage is opposite in polarity to the input voltage. And D into Vs is a buck operation. 1 minus D into Vs, you will get it for a boost converter. So in buck boost converter, you will get D divided by 1 minus D. So it is not always necessary to mention this negative sign. So it is used to show that it is called a inverted output converter. For example, when the supply voltage is 100 volt. So if D is equal to 0.1, you will get 11 volts. When D is 0.5, you will get 100 volts. And when D is 0.7, you will get more than 100 volts. So what it shows, by varying the duty cycle, you are able to get buck operation and boost operation. That is, if you see D equal to 0.5, you are getting a voltage same as the input voltage. When D is less than 0.5, you will get buck operation, and when D is greater than 0.5, you are able to get boost operation. If we draw the voltage ratio and the duty cycle graph, so this is M is V0 by Vs. Okay, so when you draw this, first thing you draw in negative direction to show that it produces a negative output, and if you take D equal to 0.5, it should be equal to 1. So this is important. You cannot draw simply draw a line. You should remember that when you draw, when D equal to 0.5, it should be equal to -1. After that, it will be increasing. So for D less than 0.5, it acts as a buck converter, and D greater than 0.5, it acts as a boost converter. Ampere second balance equation. According to that, in steady state, the average capacitor current is always 0. So during S on condition, this is the capacitor current equation. S off condition current equation. Average it, you can find the relation between inductor current and the load current. Now let us calculate the inductor current ripple. I have taken on condition. First draw the inductor voltage, which is equal to Vs during on condition and V0 during off condition. So during on condition, the inductor stores energy, so it has a positive slope, and during off condition it has a negative slope because it releases its energy to the load. And this is the current ripple del IL. We have to find what is this ripple del IL. So VL equal to Vs during on condition. So VL is equal to L into di by dt. So L into del IL by on period is dt. Equate this one, you can find what is del IL. So if you find this one, it is similar to that of a boost converter. Next, let us calculate the critical inductance. So what is critical inductance? That is the boundary condition at which, or it is the minimum inductance at which the converter operates in continuous conduction mode, and when the inductance is lower than the critical inductance, converter will go to discontinuous mode, and when inductance is more than the critical inductance, it will be in continuous conduction mode. So at boundary condition, this is called the boundary condition at which the inductor current just touches the 0 and goes up. So at boundary condition, this IL average value is equal to this half of the ripple del IL by 2. So IL equal to del IL by 2. So what is IL? You have derived from the capacitor equation. So I naught divided by 1 minus D. Del IL, you have calculated the ripple already. So substitute it, equate it, you will get the critical inductance. Calculating the output voltage ripple. So capacitor helps to reduce the ripple. We will draw the capacitor current waveform first. From the capacitor current equations which we have derived earlier, we know during the on time it is equal to I naught, and during off time it is equal to IL plus I naught. So you can draw the waveform. Let us consider the on period. What is the charge stored on the capacitor? It is equal to Q is equal to CV. What is the charge stored on this capacitor? This is a rectangular waveform. If you take the on period, it is a rectangular waveform. The area of the rectangle is given by length into breadth. So if you take the length into the breadth, so I naught into on period is dt. So I naught into dt is equal to C into del V naught. So from that, instead of I naught, I can write it as V naught by R. So we can find what is del V naught. So this is similar to that of a boost converter. So we can find that both the output voltage ripple and the current inductor current ripple are same as that of a boost converter. So the points to remember here are buck boost converter is actually a step up or down converter. Output voltage is given by D divided by 1 minus D into Vs, and it is called an inverted output converter because the output voltage polarity is opposite to that of the input voltage. And you have to observe one thing, that the input and output are not connected at any time. That is, when the switch is on or off, at both the condition input and output will not be connected. And the voltage ripple and current ripple are same as that of a boost converter, and critical inductance, if you see, it is D times the critical inductance of boost converter. And if you like the video, do subscribe to Read Electric Vehicle channel. And if you need the study material for this topic, you can visit this website. These are some of the references. Thank you.